The topic of the project is analysis and simulation of power flow in St. John's power system, and my name is Mingqi Li. My group member is Hassan. And this is our general outline about our presentation. Next, I'm planning to begin with the simple introduction of the power system in St. John's. St. John's, the capital city of the Canadian province of Newfoundland and Labrador, has an electricity system based on renewable energy, with a particular reliance on hydropower. The Churchill Falls Hydroelectric Power Station is the main power station in the area, providing the vast majority of the city's electricity needs, especially during the summer, when hydropower accounts for 80% of the total power generation. Analyzing the power flow of hydropower generation can provide data support for optimizing the design of the power grid and improving the stability of the power system. And I'm planning to introduce the electric components in the following presentation. The first one is generator. I choose to replace it with a three-phase voltage source. And the next one is boost transformer. And it could increase the voltage from the low level to a higher one. And it will be increase the voltage to 250 kilowatt. And the third one is transmission line, and I choose three-phase pi section line as the model, and I set the length to 800 kilometers. And the next one is step-down transformer. It could decrease the voltage of from the higher level to a lower level, so that all of the electricity could be applied by load. And when it comes to load, I divide it into three types. The first one is residential one, and then business one, and the final one is industrial one. So there will be three types of transformers, step-down transformers, which can decrease the voltage from the higher level to a lower level. In the following, it shows the general module architecture. The system model adapts a three-phase power supply, booster, transformer, transmission line model, and step-down transformer model. And each load is connected to the power system by different step-down transformers. And the detailed picture has been showed on the slide. And the picture below shows the detailed bus information about the power system that I've mentioned above. And in the following, I'm planning to introduce the analysis result and my tool. And this time I adopted Power Grid as my analysis tool. And select load flow analyzer in Power Grid to analyze the voltage, current, and power distribution of each node in detail. The load flow analyzer uses the power load flow function and relies on the Newton-Raphson method to provide a robust and fast solution. According to the result we got from the previous slide, we know that there was something wrong with the result, especially the reactive power. As we know, swing is selected as a three-phase voltage source, and the actual active power and reactive power will be provided according to the requirements of the system load. But it's found in the result side, the voltage source only generates 37 mV reactive power, and the actual reactive power required by the load is far greater than the provided reactive power. So the final result is negative. Because of the negative results that I've mentioned above, so we decided to add reactive power compensation devices in the transmission line to reduce voltage losses. and improve system stability. In this case, we plan to add a three-phase parallel capacitor to the industrial load. And after adding the electrical reactive power compensation devices, we made a comparison between these two types of power system, and we found that the previous negative results about the reactive power has been turned into positive one. So we know we make the final conclusion that we have to make sure that the generator could generate enough reactive power and active power to meet the load requirements. But when they cannot generate enough, we have to choose to make compensation for that. So finally, I'm planning to make a final conclusion. The feasibility of Churchill Falls hydropower station supplying power to St. John's is verified by the power flow analysis and simulation in Simulink. However, due to the use of three-phase voltage source instead of generators, the reactive power provided to the system cannot meet the load requirements. Residential loads are equivalent to pure resistance circuits, while commercial loads and industrial loads are equivalent to RL circuit. However, since industrial loads require the most reactive power compensation is provided by parallel capacitors for industrial loads so that it achieves the overall balance of the system. It's my final presentation. Thanks.